If I had a horsey, I would name it Little Cinnamon. Okay, so we are going to be looking at a fission reaction here of uranium-235 in a slow-moving neutron reaction. And as a result, we get some barium and krypton out of that and our 3 neutrons as well. But what we're asking in this problem is what is the energy released in this fission reaction listed here? Because this fission reaction is one that we have technically used, well, not we have technically used, but one that is used in our nuclear power plants, because we know there's actually like a small uranium-236 step here that happens really quick. And this means if we're using it in our power plants, we're actually getting some amount of energy kicked out at the end as well. And we're trying to figure out how much energy that is. So in order to do this, what we need to do is we need to look at our initial energy amount and our final energy amount. And if we actually, just only include our actual particles that are existing here, then the difference between the initial and final will be our energy that is added to or kicked out of the system here, okay? In order to do this, we need the masses of the neutrons and the uranium and the barium and the krypton and the neutrons again. Luckily, a few of those are given to us, all in AMUs. So let's just start working this out. There are going to be a lot of tiny decimals here, but follow along and we'll see how this goes. So first, I am going to put a big bracket, and you'll see why when we get to the end of this. And then now I'm going to start listing our masses. The mass of the neutron is 1.008665 atomic mass units. And we're going to add that to the mass of the uranium-235. It is a mass of 235.043923 atomic mass units. Now we're going to subtract all of the things we get on this the product side, or these daughters here. So minus, and then our barium is listed for us. It's the 140.914411 minus the krypton, which is 91.926156. All of these are in atomic mass units. And then minus, and this is a little annoying here, it's going to be 3 times the neutrons, because there's 3 neutrons that we have. So it's going to be 3 times the 1.008665 atomic mass units, okay? And then I'm going to close this bracket. Now, the reason why I closed this bracket is because of the following. You might remember that in an atomic mass unit, we actually have a way to convert that into mega electron volts very quickly. There are 931.5, we're just going to ignore the 0.5, MeVs per atomic mass unit. This was a neat little thing that we saw a while back in this modern section. So since these are all in atomic mass units, what I can do at the end here is just multiply by the 931 MeVs per AMU. All the AMUs go away, and I finally get this difference here in MeVs. When we run this calculation, what we'll find is that we will have a value of 173.3 MeVs, so that our initial quantity was actually larger than our final quantity here. This means that there is some extra energy that would kind of tack in at the end here, because if we wanted to kind of completely write this out, then the way this would look is there'd be like some minus energy here times the 931, and that would equal 0, because now everything has been conserved. This energy got pulled to the other side, so whenever we took this difference, this here is the energy we were looking for. So this is the amount of energy that this fission reaction is actually going to be giving off. And since it's giving off this energy, we know that it's exothermic. And that is a lot of energy there, 173.3 mega electron volts just from one neutron collision under a uranium. And we've got 3 more neutrons that are going to get kicked out. And if a moderator is in effect and these things are chaining on and we're letting this multiplication factor get away, we're going to get a lot of energy just by letting fission occur with a critical mass. And this is why nuclear reactors are so nice and efficient, because once we get this equation going here, this fission reaction, then we just keep getting energy out of it. 173.3 mega electron volts each time. So with that, this is finished. Until next time, adios and take it easy.